Volume and moles now. The volume of a gas at constant temperature and pressure is directly proportional to the number of moles of a gas. So here's the deal. The more particles that are present, the more room they need to move around if the pressure is to stay the same. So if we're forcing the pressure and temperature to stay constant, if we put more of the gas in the container, if I double the number of moles in the container, if I'm going to keep the pressure and the temperature constant, then I must also increase and double, in this case, the volume. So that's a directly proportional relationship. Okay, if you increase one, the other increases proportionally. Volume is proportional to the number of moles. V is equal to this proportionality constant times the number of moles. Again, more details on that constant coming. The direct relationship between the volume of a gas and the moles of a gas is called Avogadros law. We can show the relationship using this equation where V is proportional to N by this proportionality constant A. Directly, as we increase the number of moles, the volume increases as well. The slope of this line would give us this constant A. The final relationship we'll look at is pressure and temperature. The pressure of a gas kept at a constant number of moles in volume will increase proportionally with the temperature. In essence, the faster the molecules move by an increase in temperature, the greater the force of each collision, which increases the pressure. So if I double the temperature, the Kelvin temperature here, the collisions are more energetic and the pressure also doubles. The direct relationship between the pressure and the Kelvin temperature of a gas is known as Gay-Lussac's law, where pressure is directly proportional to temperature. If I plot a graph of pressure versus temperature, I get a direct linear relationship where the slope of the line is equal to that proportionality constant. Here's a summary of the various ways we've used to describe a gas. If we study pressure and volume, holding temperature and moles constant, we get an inverse relationship, whereas volume increases, pressure decreases. If we study volume and temperature, holding pressure and moles constant, we get a direct relationship, whereas the volume increases, so does the temperature. Volume and moles, also a direct relationship. Pressure and temperature, also a direct relationship. These four individual laws can all be combined, yielding the ideal gas law. Okay, so remember that constant we had in each of those four slides, summarizing Boyle's law, Charles' law, Avogadros' law, Gay-Lussac's law. PV is equal to a constant, V over T is equal to a constant, V over N is equal to a constant, P over T is equal to a constant. We can combine, these are all equal to the same constant, so we can combine them. So here we have PV, here we have V over T, so that would be PV over T. Here we have V over N, so PV over Tn. Okay, so combining these four yields this version of the ideal gas law. PV over NT equals a constant, which we'll call R. And I can rearrange here to get PV equals nRT. R is the ideal gas constant. This equation right here is the only one you'll need for your ideal gas problems. The value of the gas constant R depends on the units chosen for P and V. If I have units of liters and atmospheres, I'll use 0.08206. If I have liters and kilopascals, I will use 8.314. Remember that a liter kilopascal is also a meter cubed pascal. There are other values of R, but these are the two most commonly used values. When you're doing your calculations, just make sure that you choose the value of R that agrees with whatever units are in your problem. And occasionally, you'll have to change the units in your problem. So maybe you have atmospheres, moles, and degrees Celsius, and milliliters in your problem. You'll have to convert to Kelvin and liters in order to use this value of R. There are two types of ideal gas law problems that can be solved. The first involves all of the individual gas laws. You don't have to remember each of the individual gas laws. The ideal gas law will give you the relationship. All you have to do is arrange the equation so that the values in question are on the same side. Everything else is constant. The conditions in the first case must equal the conditions in the second case. Then you can solve. We'll see a few examples on the next slides. Example 1. A 4-liter volume of gas is at a pressure of 250 kilopascals. The volume of gas is decreased to 3 liters while holding its quantity and temperature fixed. What is the new pressure of the gas? So, start with the ideal gas law as you see on the left, PV equals nRT. This question deals with pressure and volume. So, we arrange pressure and volume on one side of the equation. It already is. That has to equal a constant because temperature and number of moles are fixed, we're told in the problem. So we can simply set case 1, pressure 1, volume 1, equal to pressure 2, volume 2. Those two, the before case has to be equal to the after case. And then, because we're looking for the new pressure, we just rearrange this equation to solve for P2. I divided both sides by V2 so that I have P2 by itself. I also just flipped the direction so I could read from left to right. So now I have P2 equals P1 V1 divided by V2. And then I just solve. So my starting pressure was 250 kilopascals at a volume of 4 liters. So that's P1 and V1. Then my new volume was 3 liters. So I divided by V2, 3 liters, to get 333 kilopascals. And we see that units of liters cancel here, so we're left with units of kilopascals. Okay? The only thing you have to worry about when we're doing these ratio problems is that your temperatures have to be in Kelvin. I also want to just think, does this answer make sense? We decreased the volume from 4 to 3, and the pressure increased from 250 to 333. Does that fit our understanding of Boyle's law? And it does. As you compress the gas, make the volume less, the pressure will increase. Example 2. A 250 milliliter balloon at 290 Kelvin. So we have a volume and a temperature, is heated up to 320 Kelvin at constant pressure, assuming no molecules escaped or entered, so that means N is constant. What is the new volume of the balloon? So, we are dealing in this question with temperature and volume. We have a starting temperature and volume, we have an ending temperature, and we're looking for the ending volume. So arrange the equation so that temperature and volume are on the same side. I divided by T and then moved P over, divided by P, so I have V over T is constant. This is not changing. Everything here is being held the same. So that ratio of V over T must remain constant. So whatever V over T was before, V1 over T1, has to equal that ratio after, V2 over T2. From here, we solve for V2. If we multiply both sides by T2, we get that V2 is equal to T2, the ending temperature, which is 320 Kelvin, multiplied by V1, 250 milliliters, over T1, 290 Kelvin. And we get a volume of 276 milliliters. So, if we're going to maintain a constant pressure in a closed container, if we increase the temperature, the volume must also increase. Example 3. A rigid gas canister has a volume of 18.5 liters at 13 degrees Celsius, and the pressure gauge reads 4.5 atmospheres. So we have three initial conditions here: volume, temperature in degrees Celsius, and pressure. To what temperature would the gas need to be decreased to cause the pressure to only read 3 atmospheres? So we're decreasing the pressure. Oh, I meant to change colors. We're decreasing the pressure, and we're being asked about temperature, right? That's what we're looking for. So the question deals with the temperature and pressure. Since it's a rigid container, the volume can't change. So this 18.5 liters here is constant. So let's arrange the equation so that our two variables that we're talking about are on the same side: temperature and pressure. So I moved temperature to the left and volume to the right to get this. And remember, all of this stuff is staying constant. So the ratio of pressure to temperature must remain constant. So whatever that ratio is initially, it has to be the same at the end of the change. Okay, and so we're going to rearrange this equation to solve for T2. All right, so solving for T2, I multiplied by T2 on both sides and by the inverse of this V1 over T1. So I multiplied by T1 over V1 on both sides. To isolate T2, it's equal to T1 over V1 times V2. One last thing we have to do here before we can just plug our numbers in and solve. We have T1 in this equation. We're solving for T2, but we are given a temperature in degrees Celsius, and we must perform gas law calculations in Kelvin. So the first thing I did was convert this 13 degrees Celsius into Kelvin. 13 plus 273 is 286. Plugging in those values, 286 is my initial temperature, divided by 4.5 atmospheres, my initial volume, times 3 atmospheres, gives a final temperature of 214.5 Kelvin.